Okay, this is a problem like something we did in class. Let's try to find the number of vacancies in a crystal at a certain temperature. So first, the number of vacancies depends on temperature. So maybe we do some kind of measurement. We find out that the number of vacancies at 400 degrees Celsius is 1 times 10 to the 11th. This means that 1 times 10 to the 11th lattice sites is empty, and that's 1 times 10 to the 11th per cubic centimeter. At a higher temperature, that number goes up. And that goes up because of the process that's creating these vacancies. And we'll explain more of that in a moment. So the question is, how much energy does it take to move an atom out of its lattice position and create a vacancy? And second, how many vacancies will the crystal have at 600 degrees Celsius? Okay, so first, to kick an atom out of its lattice position, what we're doing is we're taking something like an atom that's there, and we're going to bump it out and make it an interstitial. So it leaves behind a vacancy, and it becomes an interstitial atom. And a lot needs to go right for this to happen. So in order for this to get bumped out of position, I mean, all the atoms in the crystal are always moving back and forth a little bit. But it would need to get a pretty big jolt. So that neighbor had to have gotten bumped pretty hard by its neighbor. So you have to have a situation where a lot of things are going right, where it's kind of like flipping a coin and needing to get 10 heads in a row. So let's see, what are the chances of getting 10 heads in a row when you flip a coin? Well, there's a half chance for the first one, a half chance for the second one, a half chance for the third one, and so on. So this is going to be 1/2 to the 10th power, which is 1 over 2 to the 10th, which is 2 to the negative 10th. And finally, let me write this one more way. 2 to the negative 10th is e to the negative natural log of 2 times 10. So I've just changed the base there to an e. So when you see 2 to the negative 10th, think of that like that's an exponential relationship. The more heads I have to get in a row, the less likely it becomes. And this is the equation that would govern that. So this 10 is kind of like the number of heads that we have to get in a row. This formula here, something e to the negative something, is going to be a common way to describe temperature dependence. I'm trying to give you a little bit of a hand-waving explanation for why this kind of makes sense. This is the activation energy. So this is what needs to happen. So the bigger the activation energy is, that means we need that particular energy to be available for that process to occur. And so in chemistry, you made a graph of this. You graphed the average, or the kinetic energy the likelihood of a atom having a certain amount of kinetic energy as a function of that energy, or as a function of the speed. So I'm trying to draw a little bit of a line between these two relationships, one which you can easily make sense of, the odds of getting 10 heads in a row, and here are the chances of having enough energy to make this process happen. That's as much as I'm going to say about that. So I'd like to, for the rest of this video, just use this. There's a constant out front. It depends on temperature. And this R is just the same R from PV equals nRT. And we can figure out the units of it because the units of the exponent have to be no units. So we'd have the activation energy over R times T has to have no units. The units of temperature would be Kelvin. The units of activation energy, well, here it can either be joules per atom or joules per mole. Let's use this as joules per mole. That way we're consistent with the R. So the units of R must be joules per mole to cancel out the activation energy, and then per Kelvin to cancel out the temperature. Okay, and the value of that R is the 8.31 joules per mole Kelvin. Okay, so for anything that depends on temperature in this way, where there's an activation energy, the formula for it is going to be some constant times e to the negative activation energy divided by RT. So the number of vacancies per centimeter cubed is going to follow that relationship. So what I'll do is I was given two pieces of information. We'll plug in the number of vacancies for the first one, the number of vacancies for the second one, and for each one putting in the corresponding temperature in Kelvin. We have two equations, two unknowns. Solve it any way you'd like. I'm going to divide one equation by the other and get that. The a's cancel and we get this. And you know that if you have like two exponents, like e to the fifth divided by e squared, you can subtract them. So that's e to the e cubed. So in this case, I can subtract these two exponents, which gives us this, and combine it into one exponential, take the natural log of both sides, combine some terms, and we get the activation energy, in this case, to be 140,000 joules per mole. And the question said, how much energy does it take to knock one of these atoms out of its lattice position? And this is how much energy it's going to take for a mole of them. So to move one of them, we get the joules per mole and multiply it by 1 mole over 10 to the 23rd atoms, and I find out that it's going to take about 2.5 times 10 to the negative 19th joules to make this process occur for one atom. Finally, last question. How many vacancies do I expect at 600 degrees Celsius? Well, I just plug that back into our formula. A, e to the negative activation energy over R times the new temperature, but I need to have the value for A. So I go back to one of my previous equations, like this one right here, and I plug in all the values that we know, and we solve for the value of A. And now finally, we can plug that into there, and we get the value of A, e to the negative 147,000 divided by that, and I get 4.12 times 10 to the 13th vacancies per centimeter cubed.